Okay, for 8.1, we're trying to see if f of x equals 1 over x is uniformly continuous on 2 to infinity. Now, based on other examples in class, I'm going to use the idea of putting a in for the 2 to make it a little bit more understandable for now. We're going to let epsilon be greater than 0. We're going to plug in the a there, as we said. And we're choosing delta to equal a squared times epsilon. Well, we get that from our scratch work over here. We see what epsilon and delta are. And we see that x and y must be greater than this 2 or this a. If we mess around with the delta, we can get y minus x over xy. And we see that these flip because they're 1 over now. So 1 over x and 1 over y are less than or equal to 1 over a. If we put x and y together, 1 over xy, we see that it's less than or equal to 1 over a squared based on these and based on the 1 over xy we get here. So if we plug it back in, we go to the original epsilon. This is epsilon right here. Well, we see that it's less than or equal to x minus y. We get that because the absolute value here allows them to equal the same. Times a 1 over a squared, which is what we got for 1 over xy. So we see that epsilon is less than delta times 1 over a squared. If we mess around with it, we can get delta equals a squared times epsilon. So if we go back and plug that in, and we have our delta, or our epsilon, and we use our scratch work to get back to here, we get delta times 1 over xy. Well, 1 over xy again is 1 over a squared. We plug those values in, a squared cancels out and we get epsilon, which proves that f of x is uniformly continuous on a to infinity or 2 to infinity. But if we go back down and plug in the 2, instead of a, we get 2 squared, we get 1 over 4. It's the same result here. We get